Right now, something is racing through our solar system that was never born here. It's moving at 137,000 miles per hour. It came from the direction of Sagittarius, from somewhere near the center of our galaxy. And in 14 months, it will be gone forever, carrying secrets we have one chance to uncover. On July 1st, 2025, an automated telescope in Chile detected a faint smudge moving against the stars. Within 24 hours, astronomers worldwide confirmed what the numbers were screaming. This object's orbit is impossible. It's not slowing down as it approaches the sun. It's speeding up. The trajectory calculations kept failing because the computer kept assuming the object belonged to our solar system. It doesn't. This is 3I/ATLAS, the third confirmed visitor from interstellar space. The discovery almost didn't happen. For 3 weeks in June, 3I/ATLAS had been hiding in star-crowded fields, invisible among millions of other points of light. If Earth's position had been slightly different, if the telescope had been pointed elsewhere, if clouds had covered that particular observatory, we would have missed it entirely. Instead, we caught it. And humanity has roughly 1 year to learn everything we can before this cosmic messenger disappears into the void forever. Here's what makes this extraordinary. Since the solar system formed 4.6 billion years ago, we've only definitively identified 3 objects from other star systems. 3. In 2017, Oumuamua blazed through, already leaving when we spotted it. We had weeks to study it before it vanished. In 2019, 2I/Borisov gave us months of observation time. Now 3I/ATLAS is our third chance. And it's different from both predecessors in ways that are rewriting textbooks. The numbers tell a story. 3I/ATLAS is traveling retrograde, moving opposite to the planet's orbital direction, like a car driving the wrong way on a highway. Its orbital plane tilts only 5 degrees from the ecliptic, giving us an unusually long viewing window. Perihelion, closest approach to the Sun, happens October 30th, 2025, at 1.4 astronomical units, just inside Mars's orbit. It never comes closer to Earth than 1.8 astronomical units, so there's zero impact threat. But that geometry is perfect for observation. Within days of confirmation, something became clear that changed everything. 3I/ATLAS isn't a bare rock like Oumuamua. It has a coma, a fuzzy cloud of gas and dust. It's an active comet, outgassing as sunlight warms its ancient ices. The Hubble Space Telescope imaged a teardrop-shaped dust envelope 9,000 kilometers long. Inside that cocoon hides a nucleus, somewhere between 440 meters and 5.6 kilometers across. The wide range reflects how little we know about what we're dealing with. But here's where it gets strange. Spectroscopic analysis revealed chemistry unlike anything in our solar system. The ratio of carbon dioxide to water is extraordinarily high. Absorption bands of carbon monoxide ice run deeper than any solar system comet. The chemical fingerprint suggests formation temperatures below 25 Kelvin. That's minus 415 degrees Fahrenheit. This object formed in the frozen outer reaches of another planetary system, probably in that system's equivalent of our Kuiper belt, orbiting an alien sun we may never identify. Every few weeks, 3I/ATLAS brightens suddenly by 30%, then fades back. These outbursts coincide with spikes in cyanide emission and increased dust production. Fresh pockets of supervolatile ices are rotating into sunlight and explosively venting into space. The comet is revealing its interior layer by layer, like an onion unwrapping itself. Each outburst is a window into composition formed around another star billions of years ago. If current trends hold, 3I/ATLAS will peak at magnitude 10 around perihelion, bright enough for amateur astronomers with decent telescopes to photograph. Think about that. You could point a backyard telescope at a visitor from another star system and capture its light. Observatories worldwide are scheduling public viewing sessions. This is a once-in-a-lifetime event, possibly once in a civilization. The spacecraft already in our solar system are being commandeered. On October 3, 2025, 3I/ATLAS passes just 29 million kilometers from Mars. Every spacecraft at the Red Planet, ESA's Trace Gas Orbiter and Mars Express, NASA's Mars Reconnaissance Orbiter, MAVEN, even the Perseverance and Curiosity rovers will observe it. Ultraviolet spectrometers will map hydrogen escape. Infrared cameras will measure grain temperatures. We're getting a close-up view of interstellar material without launching a single new mission. Backward trajectory calculations traced 3I/ATLAS, roughly 2 million years into the past. It entered the Sun's gravitational sphere of influence with a velocity of 26 kilometers per second. Statistical models point toward a K-type dwarf star, 17 light-years away in Sagittarius, as the most likely origin. We might be looking at material from a specific stellar system, studying the products of planet formation around a star we could theoretically visit if we had the technology. Compare this to the previous interstellar visitors. Oumuamua was small, reddish, showed no gas emission, yet mysteriously accelerated. Scientists still debate whether it was a hydrogen iceberg, a nitrogen fragment, or something else entirely. Borisov looked like a normal comet, but had unusually high carbon monoxide. 3I/ATLAS has even richer carbon dioxide, stronger dust production, and a nucleus potentially 10 times larger than Oumuamua. The pattern emerging suggests that volatile-rich, icy bodies dominate the interstellar population, but the sample size is still desperately small. Theoretical models predict the Milky Way contains roughly 10 to the 26th power comet-sized wanderers, a number so large it's almost meaningless. These are the orphans of planet formation, ejected when baby giant planets gravitationally scattered their smaller siblings. Every star system with gas giants likely expelled tens of Earth masses worth of material into interstellar space. We're swimming in an invisible sea of cosmic debris. And here's the revolutionary part. We're finally detecting them at the rate theory predicted. One interstellar object every few years matches what astrophysicists calculated should pass through the inner solar system. The Vera Rubin Observatory, beginning full operations soon, should boost detection rates to dozens per year. Within a decade, we'll have a statistical sample large enough to build a taxonomy. Rocky versus icy, volatile rich versus depleted, pristine versus processed. Each interstellar object is a free sample from another star system. They're natural space probes that have traveled distances our spacecraft won't reach for millennia. By measuring isotope ratios, the variance of hydrogen, carbon, nitrogen, oxygen, we can fingerprint formation conditions around other suns. Deuterium to hydrogen ratios tell us about temperature and radiation environment. Carbon-12 to carbon-13 ratios reveal the parent star's metallicity. These objects are Rosetta Stones written in atomic nuclei. The astrobiological implications are profound. If 3I/ATLAS carries complex organic molecules, and preliminary data hints it might, it proves that life's chemical building blocks form routinely around other stars. The theory of panspermia suggests that hardy microorganisms could survive embedded in such objects, spreading life between star systems. While we probably won't detect life itself in 3I/ATLAS, every organic compound we find expands the cosmic real estate where biology might arise. Sample return is the holy grail. ESA's Comet interceptor mission, launching 2029, was designed for exactly this scenario: intercept a newly discovered long-period or interstellar comet. Engineering teams are updating flight software to handle the higher velocities that true interstellar objects possess. Concepts exist for missions that could launch on short notice, use Jupiter for gravity assists, and match velocities with incoming visitors. The challenge is immense, but not impossible. There's also the question nobody wants to ask, but everyone thinks about: could an interstellar object be artificial? 3I/ATLAS shows clear signs of natural comet activity, but future visitors might not. International protocols are being quietly developed for how to announce and study a potentially artificial interstellar object. We need clear criteria before discovery, not scrambling after. As 3I/ATLAS approaches perihelion, Earth's viewing geometry crosses the orbital plane in mid-November. We'll see the dust tail edge on, revealing three-dimensional structure impossible to study in most comets. Grain-size sorting will be visible. The tail could stretch tens of millions of kilometers, though still invisible to the naked eye. By December 2025, 3I/ATLAS will be 270 million kilometers from Earth, already fading, already accelerating back toward interstellar space. Amateur astronomers will record final light curves. Professional observatories will capture last spectra. Then it will slip below detection thresholds, continuing its billion-year journey through the galaxy. We'll have our data, petabytes of images, spectra, measurements, but the object itself will be gone. When future historians review the early 21st century, they may mark this era as the moment humanity transitioned from studying the universe passively through telescopes to actively catching physical pieces of it. We're no longer just observers. We're participants in a galactic exchange that's been happening for billions of years. Every night, 3I/ATLAS moves 7.4 million kilometers along its hyperbolic path. Every observation window that closes won't reopen. This object has been traveling for perhaps millions of years to reach this point. We have months to extract its secrets. And somewhere out there, the fourth interstellar visitor is already approaching, waiting to be discovered, carrying new mysteries from another corner of the galaxy. The universe is delivering its messages. We're finally learning how to read them.